Okay. Hello everyone. So we'll initially start this session by going through the basic nuts and grids of the theory first, or like why we'll do what we'll do in the preceding session. So we'll start ahead. So this is a basic the setup of astrophotography that we use. There are three main components here, which we have highlighted. There is the camera here that is used to capture the light that is coming from the telescope. So light comes from the telescope and it focuses it towards the camera. And then the third main component is the equatorial mount. Now, why this is essential is you need to, for capturing deep sky objects. Deep sky objects are objects that are light years away from us. So, as you must have known, the photon luminance it is proportional to 1 by r square. So, as far as you go, the amount of photons reaching you are very less, which is like very obvious. So, for that we need to capture the photons for a long time if you want a very good image. So, we need to focus the telescope on the object for a long time. But as you all know, the sky keeps moving, Earth is rotating. So, this mount, it is a motorized mount. With this, we focus on the object for a long time. We fix the coordinates. For that, we need to focus this on to the North Star, because North Star is fixed. It is focused on the Earth's rotation of axis. It is pointed towards the North Pole, the North Star. So from there, we point it towards that, and then it has two rotation axes. We'll focus on this also afterwards. First, we begin with the telescope, which is the essential part of it. Yeah, these are three different types of telescopes that we have in Kritika's inventory. No problem. These here are refractor lens. Basically, they use a lens to focus the light at the camera, essentially. And this is a Newtonian telescope, which is a reflector telescope. And then we have Cassegrain telescopes. These are the three telescopes that we have in our inventory. We mostly use refractor lens. We can also use these. These will be used in our upcoming observatory, hopefully. In the refractor lens, we use this to focus on the light. This is our Kritika's inventory basically. Cassegrain is different from refractor and reflector because it combines aspects of both of them to essentially focus the light. It is useful because it can, as you can see, Newtonian telescopes are very long. It is redundant to handle them, and it requires a lot of manpower essentially. So Cassegrain is a very compact thing that we can handle. So that's why Cassegrains are used. Now we'll come to one of the most important components. People who are coming a little late, we are just discussing the theory. The processing session hasn't started, so don't be afraid right now. So yeah, the camera. We'll start with this is a DSLR lens right here. This is the camera. The right here you can see is the lens. This is essentially acting as a telescope, as you can see. It is focusing the light onto the CCD. This is called charge coupled devices. These are in modern cameras, CMOSs are used, but we can essentially cover the gist of the theory using CCDs only, which will cover here. While we're just going through the basics of it right now. What essentially happens is in a CCD, the photons are coming towards the sensor, which is the telescope is used to focusing the photons on the sensor. Now what happens is photons excite the electrons in the sensor, which essentially results in the electron going towards this potential well, which is a pixel. Now this helps in deciding the brightness level of that particular pixel. So for example, if I get a lot of photons, the brightness level increases, and this happens throughout the whole what we refer to as the array, in the whole pixel array, and that essentially decides our image. Now one more thing I wanted to discuss is the Bayer matrix. This is the matrix that we use in front of the CCD to colorize the image. Now one thing you will be seeing is there is a lot more green here, which is important. This will be used, this is an important concept because we need to fix issues that will come with this, but this is also very essential. you will see in a cube there are two greens, one blue and one red, essentially. This is done because we calibrate it with an eye. You can see our eyes have more cones that are more receptive to the green light. So it is made to this like this to make it more perspective to our eyes. Okay, so we have gone through a lot of theory right now. So we'll do a fun question first. This is a nebula that has been captured by Anvit right here using the setup we all saw. If you know what this is, you'll get a badge basically. You can guess. Anyone here? Yeah.
Just guess by the shape of it. Guess by the shape of it.
No. No. Like the shape of it should give it away. That's a very prominent fish. No, not fish. It's not an animal. I just said it's not an animal. You can go to the Kritika account and see also.
Yeah, so this is in North America nebula. You can see the shape of North America. This is the Gulf of Mexico.
Yeah, see this red? This is Mexico. You can see this is America, this is Canada, and this is the Gulf of Mexico.
Yeah.
This is name after North America.
Nothing else.
Yes, nothing else.
Yeah.
Okay, so we'll go back to the theory right now. We'll need to wrap it up soon because the processing bit is also will take quite some time. Yeah, this is the mounts. As I was referring earlier, we have essentially two types of mounts with us. One is the Dobsonian mount. This is the beginner-friendly mount. If you have ever come to the Kritika sessions on Fridays, you must have seen us operating this. These are beginner-friendly to use because there is essentially two rotation axes. One is the y-axis and one is the z-axis. But the mount that we'll be using here and we use in most astrophotography session is the equatorial mount. Now why these are used, I gave some hints earlier. We need to follow the objects for quite some long time for deep sky objects because we want essentially more photons to hit to get a better image. So that is the basic gist of it. So to do that, we need to point this towards the North Star, and essentially what happens is, this is the coordinate system. We need to follow, let's say, this star throughout its rotation. We first, so as you can see, it moves in the two axes, the equatorial mountain. There is the right ascension moment and is the declination moment. Right ascension and declination are basically the fancy names of the coordinate system we use to identify objects in the sky.
They are like similar to latitudes and longitudes on the Earth's surface. Similar to that, it's just celestial coordinates.
Yeah, they're essentially the same, but it's the space curve, the space globe we are seeing right there. As you can see, the right ascension is referred to in this axis and declination in this. These are all technical terms. We don't need to go more into that, but if you process them and need data for them, coordinates should be referred to as these. So you need to go through them eventually. And this, why equatorial mount is used? We point this polar axis towards the north pole essentially, and then we rotate it. Once we are pointed in this, we can follow the star essentially by just moving it from one axis to the other. And when we have motorized mounts, we don't need to do that. The mount does that for us, and we just capture it. We have motorized mounts through which we capture our images. Yeah, so this was the basic hardware part. By now, all the three things we have done helped us to capture the raw file of the image, the raw photo. Now, what we need to do after that, Anvit will discuss it with you.
So now comes the software part. So the image that you see on the left is a raw photo, and the one on the right is an edited raw photo. Now you might wonder, the photo on the left, why is it so dark? Why is it so black in color? It has no color values, as you can see. It is pretty dull and dim, very boring. This is a raw file format, and it contains a lot more information that is compressed within it in layers. So I'll come to histogram when you will get to understand this in a bit more detail. But once you stretch this data, that time the information that is hidden inside it gets revealed. So that's the processing part. This is also there in normal daytime photography also, and the one in astrophotography you will realize is a bit more sophisticated. So the graph that you see over here refers to a histogram. Histogram refers to luminescence at the bottom, and here it refers to the lightness value. So basically number of pixels per luminescence. So like at zero luminescence, it will refer to how many pixels are there at this luminescence, and on 0.6 luminescence it will refer kitne pixels hai usme. So basically this is a histogram graph, and if you see in most of the astrophotographs that we capture, the data that we capture is highly focused in this particular band, the one on the left. So because of this, the data that we capture is focused on the left. It is darker in color because the luminance value is less. Now the process of stretching, that is extracting the information from this compressed data, is where the image processing aspect comes. The histogram can also be divided into 3 separate layers: RGMV, red, green and blue, and we can also selectively process the colors. So over here, yeah.
In the plot for histogram, it's shown to be a continuous curve, right?
Yes.
But then so for 0.1, for example, let's say like 30 pixels. But then the more I zoom in, I'll still find the pixel value for each decimal, each number on the number line. So there will
Yes.
be infinite.
So the histogram isn't actually a continuous curve as such, because the number of pixels on our sensor are discrete. So we have a finite number of pixels on our array, right? So it will be, for example, a 24 megapixel sensor. So there will be like those many pixels will be there in on our histogram essentially. Yeah. So let's come to the second format, that is JPEG and TIFF. So if you can see, the image on the left is a TIFF format, and the one on the right is JPEG. JPEG, you might see, is a very pixelated, blurry and compressed image. That is the most popular format that you use for photography. And this one over here is mainly used because it's better in terms of storage. So it occupies less space, so that's why I use JPEG. But the TIFF on the left hand side is similar to a RAW format. Now the difference between TIFF and RAW is the TIFF format also contains the color data, which is what we have processed, and the RAW doesn't contain that data. It is a bit more dull. So we process the raw data and later convert it into TIFF. Any questions till now about the images and the file formats? Okay.
Feel free to ask us. There are a lot of technical terms being added
Yeah.
to you right now, and this will be used in the stretching part, in the processing part later.
Yes. So here's the data. You can scan the QR code to download this data. So that will be a link, and you can download the data from the Google Drive.
And if you are not able to scan, it is also being shared on WhatsApp right now.
So another small thing is the raw image that you just saw was in a linear format. मतलब जो भी whatever the data was highly concentrated on the left hand side of the histogram. So the DSLR captures the data in a linear format, and our eyes perceive it in a logarithmic way. So whenever we stretch this image, there are multiple functions for stretching it: an arc size function or a logarithmic function, etc. There are also hyperbolic functions. So whatever stretching function to add to that linear data, you will get the data much more better. So our eyes perceive it in a logarithmic fashion. Yes.
Yeah, what he essentially said is that at the initial parts of the brightness spectrum, our eyes perceive the difference in brightness mode, which is a logarithmic scale. And the initial image, the raw image was so dark because it was divided in a linear space in 0 and between 0 to 255. And we need a logarithmic because the difference between like 0 and 50 is considered more by the human eye than what is considered by a camera. That is what it essentially said.
You might wonder why it is 0 to 255. So the reason for that is basically in an 8-bit depth image, the number of variations of brightness at 2 to the power 8, that is 256. So that is therefore 0 to 250. So that's why whatever pixel values are there, they are varying between 0 to 255. So in a 16-bit image depth, you will get 2 to the power 16. Basically. So the image will have more variation in the brightness.
Has everybody downloaded the file? Has everyone downloaded the file? We'll proceed with further then. Let me know in case it's not. Everybody is able to download the file, right? We have noted down most of the technical terms, but if we have missed out on any, please feel free to ask.
Side note, the competition, astrophotography competition, which will be conducted on 8th March, won't deal with these technical terms, so you need not remember all of these. It will be based on the processing part, which we are going to delve in just now. But this is also important for you to understand how we actually capture the data and how we process it is what we test in the competition.
Yeah, like you'll be able to understand why you are doing what you are doing in the processing bit. So we'll proceed with the processing session now. Give us 2 minutes, there are some technical difficulties.
Meanwhile, you guys can open up SiriL, the software that you have installed.
You'll also be seeing that the file is a .fit file. That is essentially similar type to TIFF file that is showed there. These fit files are especially used for astrophotography. In the meantime, you can also check out Anvik's Instagram page. He has processed a lot of images.
Okay, so you guys can open SiriL right now. and this is how the interface looks like. Now you guys can save the dataset that you have downloaded somewhere on desktop, for example here, and once you open SiriL, you can click on open, go to the place where you have saved the data, and open it.
If anybody has any problems or issues, just raise your hand and I'll be there. I'll be on a
So the black box that you see on the left is actually the image, and you can see the image is totally black, and that's because it's in the linear format. So all the data that is there in the image, all the pixel values are on the left hand side of the histogram. So if you click on image processing on the top, click on histogram transformation, you can see the pixel values are all concentrated on the left hand side of histogram. So if you want to reveal the pixel data, you have to stretch the histogram. For that, you will move this slider to the left, and you can see the histogram is getting shifted. It's getting stretched. So you can see the image on the left is getting enhanced. Basically, the pixel values are getting spread out. So if I click on apply, this stretch gets applied. You can iteratively apply this stretch and see how the image gets revealed. But before we just simply stretch this image, we want to also pre-process it. Basically, remove any artifacts and aberrations that are there in the image. I would like to explain it in a bit more depth as we go step by step. So first, you guys should close this histogram and undo this step. Now, if you see in the bottom side, there's a linear arrow over here. Click on that and click on auto stretch. Basically, the SiriL applies an auto stretch to your image, a histogram stretch, and it just stretches your image. This is just to display how the image looks. The data is still linear, but this is just to display how the image looks. Okay. Yeah, I would just repeat the process once again. So this is how the image looks on the left, a black box. So if I click on image processing and click on histogram transformation, you can see the histogram is focused on the left hand side. All the pixel values are in the linear format, so they are all concentrated to the left. I would also delve in this once more again, but for now we want to process the image, and we want to pre-process the image for any artifacts present. So first we will just click on auto stretch, and now you can see there's a really bad gradient. By gradient, what I mean, you can see in the top side the image is bright and the bottom side it is faint. So the reason for this is light pollution. So whenever you capture an image, basically you can see there's a really bad gradient over here. We want to correct this gradient so that the image is as smooth as possible. So whenever you capture these images from Earth, there are artifacts due to the atmosphere, there are light pollutions which cause this gradient. But we want to see this image as it will appear from the space, right? So for that, we would first apply a background extraction. So if you see, there are multiple settings over here, and there will be one for background extraction. Yeah, background extraction. It's at the bottom above extraction, below geometry. So in this setting now you can see this is a really complicated image. There are like many dusty regions in the background, and the star field is also very dense. So applying the extraction directly is a bit difficult. So what we want to do is identify the regions of background. So the black stripes that you can see are the background regions. This is a really bad background, the bluish region over here. So if we want to rightly identify it, we'll first invert the image. You can see the star over here at the bottom. If I click on this, the image gets inverted. This is just for display reasons where I want to identify the background regions. So now I have inverted the image, the black gets converted to white and white gets converted to black. So basically the white regions are the background regions, and I want to place my markers, the sample markers, to recognize the background. So if I manually click over here, the samples get placed. But placing them manually is a bit cumbersome. So SiriL also has an option to automatically place these background samples. So I can click on generate. Now you can see the grid that is getting generated now isn't covering the main nebula regions, the Lagoon Nebula, this one, and the Trifid Nebula. So this is good, but still there are dusty regions over here which we don't want them to get covered. So I will reduce the grid tolerance. By reducing the grid tolerance, you can selectively control the regions where you want to place these background markers. If I reduce it to, let's say, this, yeah, and if I increase it completely, more region gets covered, but we don't want to do this. So let's place it here. Now you can also control the number of samples per line. If I increase this, then the density of those samples increases. Now this is good because it can more accurately represent the background, but the software doesn't really recognize how many samples you want in a dense region. So that's why I wouldn't suggest keeping it so high. So it is better if we keep it around 16 or 17 samples per line. And the grid tolerance can be good if it's kept like around 40. Okay, so once I click generate, it will be like this. Now you can see the correction type that is getting applied over here is subtraction and division. Now what this refers to is, once I have placed these markers, SiriL will identify what type of background is there in the image. So there can be gradients in the background. Basically artificial regions that have been added due to light pollution, atmosphere. So SiriL identifies them and makes a background image. It then subtracts that image from your main image and gives you a background corrected image. There is also an option for division, but that isn't used over here specifically. So we'll just compute the background now. Okay, right. So before doing that, my bad, we have to invert it and then compute. Yeah, sorry. So first invert it and then compute. Yeah. So you can see and then you have to also apply the sample, otherwise it doesn't. So if we click on the console on the right over here, you can see the scripts and the processes that we have applied right now. So this is the background extraction process which took 600 milliseconds to complete. So yeah. Now if I undo this, you can see the difference. This is before background subtraction and this is after background subtraction. Any issues or queries till now? Okay, so if you can see the one before has bluish gradients over here, reddish gradients over here. So they are they are basically backgrounds with gradients in them, color gradients. So we don't want it to be like that. The image that you see, which can be taken from Hubble Space Telescope or James Webb Space Telescope, directly from space, won't have these gradients. So if I do a background extraction, you can see the image is a bit more neater. It is smooth and continuous all over the frame. So basically that's why we do background extraction. Okay, I hope everyone has done background extraction till now. Now we'll move to the second step, that is photometric color calibration. So this step refers to the part of image processing where you want the colors of the image to accurately represent how they look in nature. So if you click on image processing and go under color calibration, there is a color calibration manual option and a photometric color calibration. So basically what this does is, it takes your image, it recognizes the stars in your image, it matches those stars to existing catalogs of stars from observatories and telescopes all over the world, and it basically takes the it does photometry to your image and matches the flux and color intensities of the existing stars, and basically it matches the hues and the colors of your image to accurately represent how these stars would look. So I think if this is clear, I can show you how it's done. So first, the image over here, the nebula that we are processing is Messier 8, the Lagoon Nebula. So we'll enter the catalog name over here, M8. Click on find. For this you have to be connected to internet. Sorry if I didn't mention it before. So if you click on M8, it will get the right ascension and declination, that is the coordinates of the image, which we have explained before. So they are like the latitude and longitude of any target that you want to point to the sky. So these are the coordinates which SiriL has fetched from the internet. Now we want to enter the focal length and pixel size. So because this is a FITS image, it has embedded information within the image itself. So a FITS header contains the focal length of the telescope, the pixel size of the camera. So you don't need to manually input it. But let's say someone has given you an image without this data, then it is important for you to know what is the telescope's focal length, what is the pixel size, all these specifications. So now it's already there. So once this is done, you can click on OK.
M8.
M8.
What is this?
This is a nebula. It's an emission nebula. It's
Messier.
under the Messier catalog. Yes. Yes.
What if I'm trying to photograph a new object?
Yeah. So if you're trying to photograph a new object, then in that case, you will have to manually point the right ascension and declination. So in that case, you will have to see where your telescope is pointed at, note down the area and leg coordinates, and then type them manually over here. Because in that case, there's no catalog name for that target. So yeah. Okay. So PCC is done for me. If you can see, I'll just undo it to show the difference. Just zoom it a bit. So you can see the image before is a bit more yellowish and greenish, and afterwards the colors are better, they are reddish. So the reason for the color to be green is actually the Bayer matrix that we have learned before, RGGB. So the Bayer matrix contains two green pixels, so that's why you can see the initial image was a bit more green, and after PCC, photometric color calibration, the image is proper as we see through our eyes. Yes.
What if the object which we are trying to capture is then there's some change and like isn't this kind of basically comparing it with known data, then what's the point of us taking it?
Yeah, so if a target, for example, goes under a sudden change, like let's say we are photographing Crab Nebula, which is undergoing a supernova explosion currently. But a supernova like Crab Nebula takes several thousands of years to go under noticeable enough change. So basically a supernova that is getting exploded at such a large scale requires thousands of years of time for you to notice such a big difference. Now, just to answer your question, let's say we are shooting Betelgeuse and Betelgeuse undergoes a certain explosion. Yeah, then in that case we won't be able to apply PCC, photometric color calibration, because the change is drastic. Yeah, in that case we can't do that. Yes. So this is mainly to photograph targets which are static in the sky and apply this PCC to them, so that they get color calibrated according to the known catalogs and datasets. Yeah. So that the image that we capture is accurate. Okay. So now we'll apply. So yeah, just to remind you that the image is still in a linear format. Matlab, if you click on auto stretch here and I click on linear, this is how the image still looks. It isn't stretched yet. So if I click on auto stretch, it's just a preview. So the image isn't stretched yet. So now we'll apply linear denoising. Matlab, we'll basically remove the noise that is present in the background. So if I just zoom over here by clicking on plus and zoom really high on a certain region of background, you can see it is pixelated and has color noise. It has red and bluish pixels over here in the background. We want to remove them. So how is denoising done in a scientifically accurate way? You can see there's a denoising option in Photoshop also. But what that does is it applies a uniform denoising all over the image. We don't want to do that. So SiriL has an inbuilt denoising algorithm which it applies, and it applies that locally on only the background regions. So if I click on image processing now, and there's a denoising option somewhere, just a second. Yeah, noise reduction, right here, under median filter. So over here you can see the first thing is cosmetic correction, that is remove salt and pepper noise. Now what's salt and pepper doing in an astro image, you would say? It actually refers to the red and blue pixels of noise which you can see are there on any camera. Like for example, if you are trying to capture some target in extremely low light, you can see there are some certain red and blue pixels that are seen on your mobile camera also. So they refer to salt and pixel noise. They also refer to the thermal noise that come from the camera. So like sometimes when you are shooting in extremely hot conditions, that time some red pixels can be there. So basically this is to remove the hot and cold pixels of noise, salt and pepper noise basically. So, and there is also secondary denoising algorithm that you can apply, but I won't probably do this right now because it's not needed. The image is quite clean already. It has pretty less noise. As this was shot from Pench Tigerism, it's a pretty dark sky, so the image is already pretty less in noise. So I won't do a secondary stage denoising over here. I would also apply it at 0.5 intensities over there, because if I do it on completely 1 intensity, then the image will be completely smooth and the structures in the nebula can also be lost. So 0.5 is a decent enough denoising. So if I click on apply, this one takes a bit time. So the denoising is done. So for you might see it's not much noticeable change, but if you zoom in onto a really dark spot, if I undo this, you can see the denoising is getting applied over here. This is crucial because now the change might not be that evident and apparent to us, but once we apply several layers of stretching to this, that times denoising in a linear state seems really helpful. So the denoising is done now. Now we'll go to the stretching part. So if I click on auto stretch over here and click on linear now, so this is how our image still looks. It is nowhere near the final result. So now I want to apply a stretching to this. So I'll click on image processing, and there are multiple stretches that you can see. One is an arc sine stretch, one is a generalized hyperbolic transformation, and one is a histogram transformation. I will cover arc sine and histogram transformation in this tutorial, but this is also really good stretch that you can use in the competition also perhaps. Yes.
Do you guys have any doubts? It's been really fast.
Could you explain the modulation step and why do you use it?
Modulation step.
Modulation.
Can you elaborate?
Can you elaborate which modulation?
Denoising step is related to
Denoising.
and went into intensity modulation step where you decided 0.5 value.
Right, yes. I'll just go back over it. Yes. So I'll just auto stretch it again and click on what's that? Yeah, noise reduction, and there's a modulation over here of 0.5. So modulation is basically a factor of denoising that you want to apply. A factor of 1 basically represents how much intensity of denoise you want to apply. So 0.5 is basically just a factor. So if I keep it to 1, that time then the denoising that will get applied is of high intensity. Basically the entire image will get smoothened out, and the structures that are there in the background, like you can see the faint darker structures of gases and nebulas which are there over here, they can get smoothened out and you can lose that detail. So you don't want to denoise it completely. I agree that if you denoise it really high, then the image will look neat and clean, it will be smooth. But we'll also lose a bunch of detail. The small scale structures in the image will get lost. So that's why we don't overdo the denoising. We keep the modulation approximately 0.5. So yeah. Yeah, so for now we have covered, I'm just summarizing what all we have done till now. One was photometric color calibration, where you color calibrated your image to accurately represent how it looks. Second is dynamic background extraction, where you background extracted the image to remove any gradients in the image, color gradients or lightness gradients. And third was denoising. Now the next step that we'll do is stretching the image. The linear part of processing is done. Now we'll make it non-linear. Basically just stretch the data by applying various stretching functions. So if you just want to see how you can see this image by naked eyes, for example, then under linear you can see there is a logarithm function. So this is how the image would look naked eyes if your eyes were as sensitive as a camera. Obviously you won't see the nebulosity as this because the target is too faint. But if you want to see how this would look from our eyes, then this is how it would look because it is a logarithmic stretch. Now we'll keep it to linear and apply an arc size transformation. So there are total 3 transformations over here. We'll be covering arc size transformation and histogram transformation. So this is the interface for that. This is a stretch factor and this is a black point. There isn't a histogram over here visible, but you would have to imagine it that once I increase the stretch point, the histogram would broaden and the image would get stretched. The black point is to increase the blackness, that is shift the histogram to the left again. So basically the histogram is getting stretched and we are again shifting it to the left. So I stretch this like this. Now I can increase the black point slightly. Now there's one particular thing which you don't want to do. Increase the black point too much. Now you would say space is black, so I like black images. No, but if you do this, then the data in the image will get lost and you won't get the faint structures in the background. So you should ensure that you don't overdo the black point corrections. So first we'll just increase the stretch point to about 350, let's say. Apply this. Now we'll again iteratively apply this again. So we'll click on arc size transformation. The numbers are again subjective. So if you want to try, you can go ahead with 300 also. So if you see the second stretch factor that I apply, if I increase it by let's say 70, then the stretch is a bit too much because it gets multiplied over that. So basically I'll have to reduce it. Yeah. So a stretch factor of let's say 2 or 2.5 is good enough. Yeah, 2.5. And then I'll increase the black point. Yeah. Black point of 0.01 for example. I'll click on apply. So what's the difference between arc size stretch and histogram stretch? One reason for using this arc size stretch is so that the star colors are getting preserved over here. Now if you can see, the colors of the star are preserved. That is, you can easily distinguish between warm stars and cool stars over here. If I apply a histogram stretch instead of this, then the star's luminance value will be preserved, but the color data will be lost. So basically, we also apply histogram transformation after this because we want the nebula to be popped out even more. So I'll just click on image processing and histogram, and this histogram gets visible over here. And you can see the data is no longer linear. Due to an arc size transformation which we applied twice or thrice, the histogram is stretched now. But we want to stretch it even more so that the nebula gets popped up even more. So just stretch it to the left. You can see how this gets stretched and shifted to the right. Yeah. So after clicking apply, you can see while stretching it, the histogram also broadens and moves to the right. So increasing the black point ensures that the histogram gets shifted to the left. Now it is also important that you don't cross the histogram whenever increasing the black point, because whenever you do so, the information gets lost. So whenever the histogram is chipped off to the left, like you can see on the left side, the red part of the histogram is getting chipped off, that time you are losing the information. So you have to ensure that the black point is increased, ensuring that no information is lost. Okay. So I think another small round of stretch can be good. One particular thing which I would like to mention is if I zoom on this nebula, on these two, you can see the central part is extremely bright. So if I overdo this histogram stretch, that time you can see the data in the central bright part gets lost because it gets saturated. The pixel values essentially get saturated and it becomes white. So you don't want that. So you want to ensure that throughout the image, the extremely dark parts of the image and the bright parts of the image both are visible. So it is important that you don't overdo any particular stretch. Yeah. So I will just click on apply, and I think this image is good enough for now. Yes.
What was on the X and Y axis of that histogram?
Yes, so as I explained before also on the slides, the x-axis represents the luminance values of the histogram and the y-axis represents the number of pixel values. So for example, over here, the luminance value is 0. So on this 0 luminance value, you can see there are no pixels at the moment. Initially when the histogram was there, all the pixels were at a high spike concentrated on the left. So the image was in a linear format, that is, it was completely black, you could see. So this histogram ranges from 0 to 255 values. I explained the logic before that it is because of an 8-bit image depth, 2 to the power 8, that is 256. So 0 to 255 refers to the pixel values that are here. So basically corresponding to each pixel luminance value, how many pixels are there. So this is the histogram. Yeah.
You applied the some stretch twice, right?
Yes.
First you input the value as 350,
Yes.
and then you went for 2.5.
Yes.
So if we directly do like 350 into 2.5, it's 809.
Yeah, we can do that essentially,
So
but
the result will be same.
let's just try it now. Let's can try it. So basically, we're applying 700 over here. Yeah, it essentially looks the same here. Yeah. Okay, so I'll just quickly revise over the stretching part once again. So after doing the denoising and all the linear part of the processing, we are on the linear stage right now. So I'll just go over the stretching part if someone is having any doubt. So this is the arc sense transformation. We'll also cover the histogram transformation. So in this first part, you can see there's a stretch factor being applied. So if I set the value to approximately 350 over here, let's say, and apply it, and then stretch it by 2. You can see applying arc sense transformation twice, first with 350 and second time with 2, or directly applying it with 700. The difference isn't much, but it is better that you iteratively apply a particular stretch. That is so that you have more control over what you are doing. By control I mean is you don't directly stretch into an extreme state. So if I apply a black point over here, black point refers to how much of a black area you are clipping. So you don't want to overdo this. If I overdo the black point, you can see the image turns black, and some of you might find this image appealing, but data is lost over here. The small scale structures in the background might get clipped off. So this isn't an ideal way to increase the black point. Yeah. Okay, so this was mainly about the arc sense stretch. After this, we can apply a histogram transformation, which I did twice, I guess. Okay. So in the histogram transformation, you can see the histogram is on the left. It is a bit more stretched than before, and if I shift this one, stretches the midtones, and the left knob is for increasing the black point. You don't want to increase it so much that any of the region gets clipped off and information is lost. Another thing that I have covered before is the nebula has really bright regions in the center, and you don't want to increase the brightness so much that the central part gets saturated. Basically, whenever you stretch it, that time the background details get amplified more, but you lose information in the central part of the nebula. They get brightened by too much, so it's essentially just whitening the entire nebula from the center. So you are losing information over there. So you want to have a bit more controlled stretch over here. So this looks like a good enough stretch. I'll just apply it. Okay. So you can also, this part actually I should have covered before, but you can also rotate the image and basically crop the image in SiriL. You can, so the main part of SiriL is now done. We will be moving on to Gimp, but if you want, you can crop the image right over here. So this one refers to rotating the image by 90 degrees, like this. I just prefer this image, looks good in this orientation. So in space there is no up or down, so there is no particular orientation that you have of an image. So this is how it looks good for me, so I have rotated it like this. And you can also add a crop over here. One more thing that I didn't cover before was it's a good practice to crop an image before you do any of this processing. So ideally the very first thing that I should have done is done a crop over here. The reason for that is whenever you stack multiple images, I haven't gone into stacking because the time was limited for this particular session, but when you stack images, that time the borders of those images can have some artifacts. So it is good if you crop an image, but this image was already cropped, so no need to worry about that. So yeah, I want to crop this image for now, and we'll just save this as it is. So for saving, you don't want to click over here. Does anyone have any doubt, by the way, in the SiriL part? We will be moving on to Gimp. Yes. So I'll just wait for 1 minute. Rotation, right? So on the bottom right, you can see there is an option to rotate at 90 degrees by clockwise and anti-clockwise. So in space, there is no orientation of any target. There is no top or bottom. So I just prefer this image to be like this. So that's why I have rotated it like this. And you can also crop the image over here, but you can also crop it in the later stage, the Gimp. So yeah, so I'll just save this image once. There's an option to save over here, and there's also an option to save in a different name. I would just rename it slightly. Click on this, and on the desktop I would save it as let's say SiriL _ Lagoon. You can save it however you want. And the file format that you want now is TIFF. So FIT basically refers to, I told it before also, it's a format of TIFF only, but specifically for astro images. But now we'll be processing in Gimp. So Gimp supports mainly TIFF format. So that's why I'll save it to TIFF. And just save over here. And you can see the current image is actually a 32-bit floating point. it's not an 8-bit but a 32-bit image. Now Gimp doesn't support 32-bit floating point images, so we'll convert it to a 16-bit. We'll basically downgrade the image so that we can process it in Gimp. Now downgrading it by 32 to 16 is a big amount, but the difference isn't much noticeable by our eyes. So 16-bit is fine for me. Now we'll click on save, and you can see the image is saved on desktop over here, SiriL Lagoon. The image looks good as it is, but we can still modify it even more and make it pop out even more, and that's the part that we'll do in Gimp. So Gimp is basically a free version of Photoshop that is available, and you can also use it to process your own photos, daytime photos, but we'll be using it for astrophotography. So
Can you show the saving part?
yeah, I'll just go over the saving part once again. Yeah, so you click on this download part over here, save with a different name. You can rename it however you want. I've renamed it SiriL, let's say. And under supported image files, I'm going to select TIFF over here. I'm converting the file format from FITS to TIFF. Now I will click on save, and I want to save it as a 16-bit unassigned integer. That's because Gimp, the software on which we are going to work now, doesn't support 32-bit floating point. So I've converted it to this, and then I will click on save. Also note down whichever directory or place you are saving on. I've saved it on desktop for now. Okay. So before starting on Gimp, I would go through a quick review / recap of SiriL just once. So I saved it already, so I'm just going back on all these steps. So this is the linear format of the image. This will be a really quick go through. So the image on the left is a black image. It's in the linear format. You can click over here and click on logarithmic. This is how the image would look to your eyes. Now we'll just go back to linear, and this is how the basically the histogram is now. So if I click on image processing and histogram, you can see the pixel values are all concentrated on the left. Now we want to stretch this detail, and for that we will basically stretch this histogram so that the pixel values will get amplified and stretched out. But before that, we want to click on auto stretch. This is just a preview option. So the image is still in a linear format, and we want to apply multiple layers of pre-processing now. So this is just a preview option, and we'll first do color calibration. So under image processing, color calibration, we'll click on photometric color calibration. What this refers to is your current image that you have captured. SiriL recognizes the stars in the image. This process is called astrometry, by the way. It recognizes those stars, it matches those to the known catalog of stars of that target, and it color calibrates your image so that it is accurate. It accurately represents how the image would be. So the target that we have shot over here is Messier 8, M8, that is the Lagoon Nebula. So I will type over here M8, click on find. For this you have to be connected to the internet. So I click on M8.
Yeah.
It's important. Yeah.
What if you take a much wider shot?
If I take a much
Wider shot.
wider image. Yeah, so the PCC can be applied to even wide field images. So for example, you capture an image of Milky Way, for example, let's say, and it spans across the sky, right? So it can be used in that situation also. Now PCC isn't applicable for extremely wide images where it spans from horizon to horizon, because in that case you might have noticed in a wide angle lens the image gets morphed slightly. Like whenever you try to use a wide angle lens and keep it close to somebody's face, that time his face can get very weirded out. So something similar happens to Milky Way also. So whenever you shoot Milky Way that is spanning throughout the sky, so those images PCC can't be applied. But a certain region of Milky Way that is wide enough, then you can definitely apply that. So the amount of wideness of the image basically is represented by the focal length. So if a telescope is of 1000 mm focal length, it has more magnification. So a smaller region of the sky is covered. And if a focal length is, let's say, 15 mm, a small DSLR lens, then a wider region of the sky is covered. So PCC can be applied to like 11 mm or 10 mm lenses, wide field DSLR lenses. So yeah, that's the downside of this particular process. In that case, you will have to apply manual color calibration. Yeah. So this was it with PCC. You can apply PCC over here now. And also you might have noticed there's no particular order to apply PCC and DBE. Both processes can be interchanged, but usually it is suggested to apply PCC, photometric color calibration, after DBE. So it's good if I do it the other way around, but there's not a defined order to do this. The other processes have an order, like denoising should be done when the data is not stretched. So the order is important. But for background extraction and color calibration, they can be switched around. Okay, so you can see the stars are color calibrated. And after this, I will go for background extraction. So under image processing, under geometry and above extraction, there's an option for background extraction. So I can manually place points in the background. So it is important to recognize the regions of the background. The black parts are the background and the brighter parts are the nebulae. So I don't want to place my points over here, let's say. It's important that I place the points on the background markers only. So in the darker regions of the sky. So if I click on generate, SiriL would automatically generate these points because I can't just keep placing these points everywhere. It's just too tiring. So I click on generate, generates a grid of background markers, samples. If I increase the grid tolerance to 2.5 and generate, it will be less sensitive to the regions of brighter regions of nebulae. So I don't want to do this because there is nebulae in the background here also. So I would decrease this background and the darker regions are getting covered. Now if you would see over here, it is hard for me to distinguish the black regions of this. So it's a good practice to invert this image first. Basically click on the star over here. It inverts the image. This is just for preview. Haven't done any permanent changes over here. The white regions of the image are the background now, and I can recognize them easily and generate a background. By increasing the sample per line, I can increase the density of samples, but it's better to keep it around 17, let's say, 17, 18. Yeah. If I click on compute background, first invert it and then compute the background and then click on apply, you can see the background is a lot more smooth now. Here you can see the background has gradients over here, bluish regions over here, reddish regions over here, and it's not a smooth background. This is because of atmospheric defects and light pollution. If I capture this image from space, then the image will be smooth and it will be like this. So this is how the image would look from space essentially. So yeah, so mainly this was this, and after that I covered stretching, and stretching can be done by arc science and histogram. I won't go through it a bit again because it's a bit repetitive now. So yeah, so I have saved the image now, and I'll open Gimp now, and so you can open Gimp and we'll use the stretched image from SiriL. Takes time to open. Okay, so this is the Gimp interface. I click on file, open, and you can see in desktop the latest TIFF file that was created from SiriL, SiriL.lagoon. I'll open this, and it is important to convert the file so that Gimp recognizes the colors. So the image in SiriL was a fit file and it was converted to TIFF. So the colors that were embedded in the image have to be converted to a recognizable format in Gimp. So I will convert it over here, and now the image is exported to Gimp. You can click on Control and yeah. So now you can also crop the image over here. The icons on the left hand side are what we are going to use. The first one is to move the image around. The one below it is a crop option. So if I drag from here to the bottom, a square will get selected. I can reduce the size of this square and crop the image as I want. There's a certain region of nebula over here, but it's at the edge actually. So that distracts our attention from the main nebula. So I wouldn't want it in my main image. And click on enter. The image gets cropped. Yeah. So now we are going to enhance the colors and details of this image even more. That is by going to colors and we'll click on curves. Increase the size of this. Here the curves transformation. So you can see the histogram that was there in SiriL is represented over here, and you can modify the histogram in a more free-handed way over here than SiriL. So this software is similar to Photoshop. So you can do changes over here as your own will. So there are ways to process it like extremely aggressively also. Like you can increase the colors as you want. You can increase the saturation so it skyrockets the roof. But the image would look extremely bad because it won't be natural and it won't be as you want it. So there are bad ways to process it also. And these are the factors on which we'll also judge in the competition also. So aggressive ways of processing an image are highly discouraged. So basically this is the histogram. If I draw a curve over here, stretch this point over here, take it to the top, stretch this point over here, take it to the bottom, you can see the contrast of the image increases. Now you can easily overdo this. Increase it more, decrease it more, and you can see the space gets darkened. It might look good for you for now, but the contrast of this image is highly increased. The regions near the nebula, like I said before, have lost their information. So in the center of the nebula, the highlights have blown out. Basically the pixel values have saturated. So this is a bad way to stretch it. This is overdoing it. Being a bit more subtle with this is a better job. So I would apply a mild S curve over here. This is an S curve and it stretches the histogram. There are also ways to stretch it manually by tuning the red, green and blue. You can explore it later on, but for now I'll just apply this S curve. Okay. And the curves, you can also apply a general brightening curve by shifting it to the top. Again, won't do it too much because this nebula will get blown out. By blown out I mean the highlights would be blown. The information will be lost. So yeah. Now I can click on colors and click on color balance. So again, doing this over is a really very easy job and it can ruin your image very easily. If I change this color to the completely right hand side, the red regions of this image will get amplified. Just to show you this. This image can look extremely bad, so you don't want to overdo this. You have to ensure that the image looks beautiful and it also accurately represents how the nebula is as it is. So the output that we got from photometric color calibration has given us a really scientifically accurate color in the image. But so you don't want to modify it too much. So this is the subjective part where you can tweak around these colors and modify the image as you want. So I think this looks good enough. I'll click on OK. So if I go under colors. There's an option for saturation also. I can increase the saturation to the maximum, but then the colors would be blown up, and some of you might think this is a good image, but it actually isn't, because the colors are unnaturally brightened. So this is a bad way to do this. I would bump up the saturation by at max 2, not even 2, 1.5, let's say, 1.5 at max. Sometimes highly saturated images are good for Instagram to get views and all, but honestly I don't find it appealing. So 1.4 is a good stretch, and click on OK. And if you can see under colors, there are multiple settings that you can explore, but the image looks good as it is. So I would save this. For saving it, I will click on export as. There is an option for save as also, but if you save this, a Gimp instance will be saved. So you shouldn't click on save as, you should click on export as. Now under this, you can change the name of this. Let's name it Lagoon Gimp. And the file format that we want is JPEG. So finally, we want to upload it on social media, and also we can't afford high memory storage file formats like TIFF or FIT. We want to convert it into JPEG. So in the end, the image that we get is compressed only, but we'll have to save it in JPEG. Yeah. So yeah, we'll click on export and save it on desktop only. And when you click on export, you can set the quality of the JPEG. A high quality JPEG would have less compression. I have explained JPEG compression before also. So if I keep it a low quality, the image will be more pixelated. It will occupy less storage, but 80 is good for now, I guess. So, and export. So this is the final JPEG processed image that we have, Lagoon_Gimp. If you open it like this, can be visible. So the process of processing an astrophotograph is actually a really long process. So the process that I have undergone right now is really elementary and covers the basic aspects of it. But if you want to process this image, I would say exploring other settings in Gimp are also advisable. So there are multiple settings over here which you can go through, which can give you a lot more control over this. Yes. Yeah, so after clicking on export as, you can rename the file format. Click on select file type, select the file as JPEG, and then click on export. And then it gets saved in whatever directory you want. Yeah. So after doing that, there will be an option to select the quality basically. So if you set the quality low, the image will be more compressed and it will be more pixelated. And if you set it high, the image will occupy more storage. Any doubts? Does anyone have any doubts currently? Any process or any part of processing that you haven't understood? Yes, so I would just quickly cover up one summary of what all has been covered in this session. Yes, so I would just quickly go over whatever we have covered in Gimp also. So in Gimp we first rotated and cropped the image, then we did curves adjustments, then we also did color balance and later tweaked the saturations a bit and then saved our image. So Gimp was to just enhance the image a bit more, and as you can see these are the details of the astrophotography.
So I will just go through the details of the astrophotography competition happening in the BG Tech Week. There will be prizes worth 7,000 rupees. So it will be distributed to us first, second, third. We will release practice data sets soon. They will be released on webmails and WhatsApps. The competition date is on the 8th of March, this Saturday. The timing will be 7 p.m. It will happen right here in LC 101. We have also uploaded astrophotography process these sessions on our YouTube channel. There's a link for that. There are like 3 videos. 2 of them are deep sky images. One of them is a planetary image. So you can scan the QR code.
If anyone has doubts, I can come over to you.
Also WhatsApp on
We have also shared a feedback form for today's sessions. It has been shared on the WhatsApp group.
It's not, we have to show it.
You have to show it? Everybody, is someone still scanning this? This was a session that has been uploaded on YouTube.
We will also put this link on WhatsApp group or something. So
Yeah, we'll share this link and also search Kritika IITV on YouTube and you'll get these
Yeah.
sessions.
They are on our YouTube channel.
Yeah.
So
Yeah, these are some other YouTube channels that post videos of processing on deep sky objects. Me personally, have also gone through some of them. One of them being Andromeda and all. These are very helpful. These are what taught us, what we are teaching you. So, yeah.
So this particular part I just cover it a bit quickly. So as you could see, the DSLR cameras and all have get color images directly. That is because of the Bayer matrix on them. Now the images that Hubble and JWST capture are actually grayscale images. So you place a filter in front of the camera directly. So a red filter, a green filter or a blue filter, and it captures one grayscale image. Each image corresponds to the color. So basically a red, a filter with red color, a filter with blue color and a green color. Then you later combine these monochromatic images in SiriL, and you can process images from Hubble and JWST. Because of time limitations, we couldn't cover this aspect in the current workshop, but we have very thoroughly covered this processing of Hubble and JWST on our astrophotography learner space. The QR that you guys just scanned or the link which can be available on our YouTube channel, Kritika YouTube. So I would just quickly go through how you can access such images. So these images are publicly available on Hubble Legacy Archive. So if you search over here, Hubble Legacy Archive, the very first link that comes, you can click on enter site here. and type in any nebula or galaxy that you want. So let's say I take M51, that is the Whirlpool galaxy, and click on images. There will be multiple images displayed of this galaxy. So these are the actual raw images that have been captured by the Hubble Space Telescope. Now, as you can see, these images are grayscale. They refer to each filter that they have been used with. The filter name refers to the nanometer wavelength of light that has been captured. And if you go down, there is also a combined raw image. So what you have learned in this workshop is processing color images and stretching them. You can directly process these raw linear images of Hubble Space Telescope and use whatever you have learned in this current workshop to process these images, the colored ones. If you want to learn mono processing, then you can refer to our YouTube channel. Right. We'll also send a link of Hubble Legacy Archive. All these links will be like compiled in a document and sent later. Okay, so thank you all for coming to this session, and we would also upload a QR code for your feedback for this astrophotography
We'll show the
session.
QR code right now.
Yeah, we'll just send the QR code. Please scan this QR code and put your feedback. Yeah. Thanks a lot. Yeah, also guys, when you post these processed images on your Instagram, don't forget to tag Kritika IIT Bombay whenever you put these processed images. Yeah, if you want.
We will be posted.
Yeah.
Please scan.
This is the QR code to the feedback form. Kindly tell us how you felt about this session.
I hope you all learned something new. Credits to Anvit for taking such a wonderful session. Can we please have a round of applause for him?
Yes.